Hello, welcome to the lectures on Module 8, External Flows. This is covered in Chapter 9 of the textbook in sections 9.1 to 9.4. In this unit, we are going to look at flow over immersed bodies. These could be examples like airplanes, flow around aeroplanes, cars, ships, fish, raindrops, sand, anything over which the flow goes around. So if you have like an object, if you have a flow that is going around an object, that's what we would refer to as external flows or flow over immersed bodies. If you contrast this with what we learnt in Module 7, where we looked at flow through conduits or pipes, where you are talking about flow that is bounded by the walls of the pipe. Here, we usually have the flow to be in contact with the structure. On one side, on one end it is in contact with the structure, and the other side or the other end is usually infinity or free stream. That is, they are semi-infinite flows where one side is finite, it is in contact with the wall, and the other side is unbounded or merges into the free stream eventually. So we are going to look at this type of flows or external flows in this unit, and I want to begin by classifying these flows as based on their spatial configuration or based on their spatial characteristics. This is illustrated in figure 9.2 in the textbook, and what I want to mention is that there are three classifications that one could make. It is called two-dimensional, axisymmetric, and three-dimensional. So let's see what those are. Okay. So if we take the first type, which is two-dimensional flows. So suppose I have a cylinder that I draw here, its cross section, and the cylinder's length comes out of the plane of the board and goes into the plane of the board infinitely in both directions. That is, I have an infinite cylinder whose cross section looks like a circle, and I am having a flow that is going over the cylinder from left to right. You can imagine this to be like a very long telephone cable or electrical wire that is hanging, and the wind is blowing over the infinite cylinder. In both directions, the flow is just crossing the cylinder, okay, at every location, including the plane of the board, and the flow here has a velocity that can be resolved into components, but it has no significant component perpendicular to the board. That is, the flow here travels as though it is traveling on a sheet of paper or on a plane, and it has only two coordinates that are non-trivial or non-zero, and we call such flows two-dimensional flows. That is, they are described by two spatial coordinates, and the third component, the z component, is non-existent. Such a flow where one of the dimensions, it is usually the case when one of the spatial dimensions or spatial extents is infinite. That is another way of saying it is much longer than the other two dimensions. It is much longer than the other two dimensions. In this case, for the infinite cylinder, the length of the cylinder, if it's much greater than the diameter, then we can approximate this flow as the flow over an infinite cylinder, and it is a two-dimensional flow. Now if you think of this infinite cylinder, nothing is really infinity in reality. If you take a telephone pole wire, if you take a wire that is extending in this direction, if you are near the middle of the wire, far away from the edges, you can reasonably call this flow a two-dimensional flow. If you are near the edge, this flow ceases to be a two-dimensional flow, because let's say the cylinder ends about here, the flow goes over the cylinder, and near the edge it has to go in the other direction as well. So you are starting to have a component that is perpendicular to the plane, and then it ceases to be a two-dimensional flow. So if I were to cautiously say, if I were to ask this question, is the flow over a telephone wire or a electrical cable that is hanging between poles a 2D flow? Can I call it a 2D flow? That's the question. Okay, is it a 2D flow? That is, if I draw a picture, here is pole 1, here is pole 2, and I have a wire that's hanging between these two. And let's say the wind is blowing in this plane, the wind is blowing over the pole. If I am considering regions that are reasonably near the middle, over here the flow can be considered 2D, because they are far away from the edge. The length is much longer than the diameter of the wire. If I am considering these areas near the edge, at these locations, it has to be considered a three-dimensional flow, because the flow here is dominated by the flow around the pole, not only over the pole. So where you call a flow two-dimensional is subjective. If one of the dimensions is reasonably much longer than the other two, then it is more or less a two-dimensional flow. If that is not the case, if the length of the cylinder in this part here, if it is comparable to the diameter, or if it is closer to an edge which can induce flow to turn around, then it's not a two-dimensional flow. That makes it a three-dimensional flow. So now we have a way to define 3D flows, which is basically saying flows without any kind of symmetry. That is, if you have a velocity, it depends on all three components. There is no component which is 0, or no component which has a fixed value. It is a flow with no obvious symmetry, and we call such flows three-dimensional flows. Okay. So we talked about 2D, we talked about 3D in figure 9.1. There is also a classification called axisymmetric flows. Axisymmetric flows. And what are those? That is, if I take an object flow over an axisymmetric object, if I take a flow over an axisymmetric object, which in the book, the example given is like a bullet. If you have a bullet whose front view, or if I have a bullet and I have a flow over a bullet, okay, if I draw the front view looks like a circle, and a circle is an axisymmetric shape, meaning it has in every direction it looks the same. That's what we call axisymmetry. In every direction it looks the same, or in other words, there is no dependence on the angle theta. That is, in every direction it is the same. there is no dependence on the polar angle. That's what we call as axisymmetric. Okay, so flow over an axisymmetric object, it goes around the object. Okay, it goes around the object, but in every cross section, in every angle that I slice this pie, the flow looks the same. So the flow depends on a radial component, it depends on a axial component, but the flow doesn't have a polar or azimuthal component, and this dependence is also absent. That is, nothing in the flow depends on the polar angle, and such flows are called axisymmetric flows. These are usually flow over an axisymmetric object, although we have to be careful. Most of the time, only laminar flows are axisymmetric. Turbulent flows sometimes can be three-dimensional even when they are over an axisymmetric shape. That's the nature of turbulence. It becomes three-dimensional even if your geometry is two-dimensional, even if your geometry can be described by only two variables. Okay, so that is the distinction between 2D, 3D and axisymmetric. The next important aspect about flows over shapes is that if you have a flow that is going around a structure, usually or not usually, always the flow exerts a force on the structure. That is, if you have, you know this from everyday life in so many instances. If you are driving a car, you press the gas pedal, you accelerate forward. If you stop pressing the accelerator, no matter what speed you are, eventually your car will come to a stop because the friction in the road, the friction offered by the air that flows past the car will slow it down. If you are swimming, you know that water exerts resistance on you. If you are going on an airplane, the way the airfoils are shaped creates a lift force that lifts the aeroplane against gravity and keeps you airborne. So we all know that the common manifestation of fluid forces on structures, they can be classified into two terms. It's called drag and lift. That is, if you have a structure, let's say I think of an airfoil, and I have a flow, a uniform flow that is far away from the airfoil. When it comes near, it goes around the airfoil, something like this. Okay, the fluid obviously pushes this airfoil in this direction. That is, it's trying to push the object, and the object is trying to move this way, let's say. So the drag force is the force exerted by the fluid on an object along or parallel to the direction of motion of the object, not the flow. That is, if I am trying to move this way, if my velocity is directed this way, drag force is the force that is acting parallel or actually opposite to the direction of motion. This would be my drag force. So if I put a symbol here, drag force exerted by the fluid on an object. Drag is the force, or drag is the force exerted by the fluid on an object It is exactly in the same line but opposite sense. Anti-parallel to the direction of motion of the object. Lift, on the other hand, if I am trying to move this way, fluid is trying to move this way, it is the force in the direction perpendicular to the direction of motion. So lift force is the force exerted by the fluid on an object perpendicular to the direction of motion of the object. Lift is the force that is perpendicular to the direction of motion of the object. The symbols we use, sometimes we use FD, we use FL, or D vector and L vector. So those are two important manifestations of fluid flows around objects: drag force and lift force. How to calculate the drag force, how to calculate the lift force comes from basic ideas of knowing what is the pressure distribution, what is the shear force distribution, and then trying to evaluate it as a surface integral. We will do that in due course. So if you look at figure 9.3 and 9.4, what we have there is a force balance, is basically a way to calculate the drag force and lift force on an object that is at an angle theta to the direction of fluid flow. That is, if you have some object, okay, it could be an arbitrarily shaped object, or it could be the airfoil that I drew. Okay, if suppose the fluids, if suppose the direction of motion of the airfoil is in this direction, and the angle between the two given by theta, we want a relationship for the drag force and the lift force, and that's provided in equation 9.1 and 9.2. Equation 9.1 and 9.2, which you can simply understand that drag and lift, they are ultimately forces. Those forces arise because the fluid exerts pressure. Pressure is always normal to a surface. Pressure is always normal to a surface. The fact that pressure on one side is higher than the pressure on the other side leads to lift. And then there is also shear force, that is at every point along the surface there is a shear force, a shear stress. So you have pressure normal to the surface and compressive, and shear that is tangential to a surface and related to viscosity, so we call it viscous shear. by integrating the pressure distribution and the shear distribution and resolving it along the direction of fluid flow and the perpendicular to the direction of fluid flow or our reference directions, we can calculate the drag and lift force, which are given to be P cos theta dA plus the wall shear sin theta dA. This is the drag force in this direction and the lift force in this direction. Okay, and the lift force, which is equation 9.2, is minus P sin theta dA plus tau W or wall shear cos theta dA. Now what is dA? dA is the area, dA is the integral is evaluated over the area of the object exposed to fluid flow. dA is the area of the object exposed to the fluid flow, which is basically this area. This is a cross section, remember. If you want the area, you should understand what is called the span width. That is, if this airfoil extends, let's say 1 foot or 100 foot or 10 foot in this direction, it's the area that forms that over which the fluid flows. Okay, so if this were a very long airfoil, it's a wing, and you are calculating the drag and lift near the middle of the wing, you would just consider this to be a 2D flow. If this wing has, let's say, a finite length, you would consider this to be a 3D flow. Ultimately, these two quantities, pressure distribution and shear stress distribution, they have to be known. They need to be known